Hello everyone and welcome to today's webinar. My name is Chris Paulsworth and I'm the drying expert here at Hoscal Micron Powder System. During today's webinar we will be discussing the basics of drying principles, theories for flash, vacuum, and freeze drying, various types of dryers that we offer, and we'll finish up with a review of the drying systems for a variety of material applications. So to begin, what is drying? Quite simply, drying is the removal of water or other liquids from a solid. So you'll start with the liquids and the solids mixed together, and you'll end up with two separate finished products, a liquid and a solid. So how do you remove this liquid from this solid? You can do it by mechanical means, and this is often filtration or centrifugation. For filtration, what you're doing is you have the liquid and the solid, and you use force to push it against the membrane. The liquid will pass through the membrane while the powder will be left behind on the filter membrane. For centrifugation, what you do is you will rotate the mixture of your liquid and your powder, and the powder will move to the outside and the liquid will move to the inside based on density. This is going to allow you to separate your powder from your liquid. So, mechanical drying is using the force to separate the solids and the liquids. The advantages of mechanical drying are low energy use. The disadvantages are that there's often a limit on the final moisture content that you can obtain using these methods. So moving on, you can also use thermodynamics to remove your liquid from your solid. You can do this using evaporation, which is flash and vacuum drying, and sublimation, which is also called lyophilization, which is freeze drying. So in this, you start the same way with your liquid and your product, and then you turn the liquid into a vapor, and you can then separate it easily from your dry solids. So looking at thermodynamic drying, you're going to be changing the liquid to a vapor, possibly after freezing it first. And the advantages are low final moisture content is possible, and the disadvantages are often that it's higher energy usage. So this is a phase diagram for water. If you look, you can see there's three phases for water. You have liquid water, water vapor, and ice. We will exist somewhere on this line at 1 atmosphere and about 20 degrees C, somewhere right around here. Now, as you change your operating conditions, so as you change your pressure and temperature, what you're doing is moving around on this diagram. So we'll be using this diagram for the rest of the presentation, so you can see it's very similar. The green is the liquid, the blue area indicates the solid, and the orangish yellow area, is going to be the vapor. And then standard operating conditions are going to be right here. And then you can also see on this diagram that this point indicates the boiling point, and this point indicates the freezing point at 1 atmosphere. And you've got 0 degrees C and 100 degrees C, which you should all be familiar with. So if your goal is to go from a liquid to a vapor, you're going to be performing evaporation. You can do this in two ways. You can heat the mixture, and that is going to take you past the boiling point, and it's going to cause you to generate your vapor, basically. You can also decrease the pressure, and by decreasing the pressure, what you're going to do is you're going to reach the point where you can boil the temperature at whatever temperature that liquid is at. So if you start at room temperature and you reduce the pressure, eventually you'll get to the point where at room temperature that liquid will boil and you will obtain your vapor. If you want to do lyophilization or freeze drying, you have a slightly more complicated process. The goal here, what you want to do is you want to first start by freezing your product. So you'll start at room temperature, you'll cool the product until you have a solid mass. You'll then decrease the pressure, and notice you want to decrease the pressure so so low that when you heat the product back up, you do not pass through this green area. So you can notice that the heating arrow is going to cross directly from the solid to a vapor and not pass through the liquid phase. This is important because you want sublimation. What would happen here is you would have melting and then vaporization or evaporation, which is not what you want to occur. You want the product to go strictly from a solid to a vapor. So we're talking about heating and cooling the system. How does that occur? So what happens is you are putting energy into the system or removing energy into the system, from the system, and that's going to be heating and cooling it. The way that that's going to work is the energy required is equal to the amount of temperature change you would like to occur, the specific heat capacity, times the mass. And now this slide shows some examples of the specific heat capacity. You can see that, and I should also note that these are at a constant pressure, so you're talking about atmospheric pressure. But you can see that often the heat capacity will change dependent on the temperature, but not much. So at 20 degrees C, you're at 4.183. At 100 degrees C, you're at 4.219 kilojoules per kilogram degree Kelvin. Another thing to note from this slide is that water has a higher specific heat capacity than ethanol. So if you want to change the temperature of water, you're going to have to put in more energy than you would for ethanol. So you've now heated up your water and powder mixture, and you're at that point where you can then begin evaporation. So you're going to be continuing to put energy into the system. And what's going to happen is you need to generate enough energy in the system that you can cause that liquid to turn into a vapor. So the energy requirement is equal to the latent heat of vaporization, or whatever phase change you want to occur, times the mass. And then these are examples of the common ones. So you have the latent heat of fusion, which is going from a liquid to a solid, the latent heat of vaporization, which is going from a liquid to a vapor, and the latent heat of sublimation, which is going from a solid to a vapor. So examples of the latent heat. For ethanol, you can see that example, and then you can also see how it compares to the specific heat. You can see that it's much higher. For water, if you compare the the latent heat of vaporization of water to the latent heat of vaporization of ethanol, you can see that water has a much higher amount of energy for the same amount of mass. So this is per kilogram. So to take 1 kilogram of water from a liquid to a vapor is going to take a lot more energy than it is for that same mass, or that same mass amount of ethanol. Another interesting point, so if you look at water, the maximum specific heat for water between 0 and 100 degrees C just happens to fall at 100 degrees C. So if you take that value and you were to assume it's constant between 0 and 100, and then calculate the amount of energy it's going to take for 1 kilogram of water to go from 0 degrees C to 100 degrees C, you can see that you're only going to use 421.9 kilojoules. Now you can compare that to taking that same kilogram of water and evaporating it. You can see that you're going to need much, much, much more energy to evaporate that water than you would to do that temperature range for that temperature change, for that whole range of temperature. Also shown here is the latent heat of fusion. So you have to remove the energy, this much energy from the system in order to get the liquid to turn into a solid. But you can also compare that to the vaporization and the amount of energy to go from 0 to 100 degrees C. So when we're talking about removing this moisture, it's important to consider what type of moisture is it. And we often look at two types of moisture for these drying systems. We look at surface moisture and bound and entrapped moisture. The surface moisture is going to be all this moisture that's going to be on the outside of the particles. Also, free moisture, if there's any drops out here, those would also fall into this same category. But this is moisture where the energy can get to it very easily. It's readily accessible. So you have energy, you start adding energy into this system, and this water is right there, and that energy will just transfer right into it. The other kind of moisture you're looking at is bound and entrapped moisture. So if your product has crevices or pores, water or whatever liquid you're using, is going to get within those, get into those cracks and those crevices and those pores and get down in deep. Now that water or that liquid is going to be much harder to remove than this moisture on the top. So we consider that to be entrapped moisture. Now this comes into play when you look at the drying rate. So you start here and you are adding heat into your product. You're going to get constant rate drying as you get all that easy to get moisture. So all that surface moisture and any free moisture, that's going to come off at a constant rate continually as you add heat. Once you get all that easy moisture, what's going to happen is that the rate is going to fall off. So you're going to have to get that moisture that's very deep in between the particles, and then you're going to have to get that moisture that's actually inside the particles themselves. So what's going to happen is if you look at the drying rate, it can be divided into two sections, constant rate drying and falling rate drying. So constant rate is that easy to get moisture, and falling rate is going to be that hard to get moisture. This is an example that I think pretty clearly shows the two phases, constant rate drying and falling rate drying. So if you look at the green curve is the moisture content of your product. So you can see it's going to start at a high amount, and then as you start drying your product, it's going to fall off. It's going to fall pretty steadily as time, so you have time down here. It's going to fall pretty steadily as you continue to dry your product. You're going to get to a point where you've gotten all that easy to get moisture, and then you're going to see that the slope is going to change, and you're going to enter the falling rate phase. During the falling rate phase, you're going to get that hard-to-get moisture until you obtain your final dryness. That is going to be whatever you need. So, how are we going to add that energy in? So we've talked about the energy required, and we've talked about, that changing, the phase change. So how do we add that energy in? You're going to add that energy in two ways. You're going to add it via either direct drying or indirect drying. For direct drying, which we also call convective drying, you're going to have your product and you're going to add the heating media directly into it. So in this case, and most often, this is hot gas. So you have hot gas coming in. It's going to be in direct contact with your product. It's going to be intermingling in there. You're going to get really good contact and really good transfer of the energy from this hot gas into this product. The other way you can do it is indirect drying, which we also call conductive drying. For indirect drying, you've got a heating jacket, and this heating jacket is going to have this heating media flowing through it. And your product is going to be in some sort of vessel or some sort of enclosed container. That jacket is going to allow the heating media to transfer through the wall of the vessel the energy into the product. So you never have your heating media in direct contact with your product. You're conducting the energy through the wall. Only the product that's going to be at the edge is going to really see that energy readily. So this is a much less efficient process than this, and it's going to be a much slower process, and it's going to be harder to get this heat into the bulk of your product. So we talked about getting the energy into the product. Now we'll go into the different types of drying. So we'll start with vacuum drying. Why drying at vacuum conditions? Drying at vacuum conditions is going to be drying at a low temperature. So it really is good for products that are temperature sensitive. It's also good because it can obtain a low moisture content, and it's good for getting out entrapped liquid. It's a batch process, and you can take the time to really dry that product out if need be. So it's good for those items. It's controlled and contained process, and this hits on those last 2 points too. It's going to allow you to do solvent recovery, and it's also going to allow you to contain and control your process for toxic, flammable, or explosive products. Looking at vacuum drying, what's actually occurring is that, and it's not as clear on the phase diagram as it is on the vapor pressure curve. So this is a vapor pressure curve, and this is vapor pressure curves for water and a bunch of other solvents, or a few other solvents, excuse me. So if you look here at 1,000 millibar, you're basically at atmospheric pressure, and the boiling temperature of water is 100 degrees C at atmospheric pressure, excuse me. As you reduce the pressure, what you're doing is you're reducing the temperature that the water will boil at. So if you keep reducing the pressure, once you get down to about 250 or so millibars, at 65 degrees C, your water will boil. So say your product can only take the temperature of up to maybe 75 degrees C, then vacuum drying would be a good solution because you only need to heat up to 65 degrees C to be able to evaporate off that water. So you can see how this can be advantageous. And also shown, and it's good here, is that the trend is pretty consistent for all liquids. So as you reduce the pressure, the vapor curve is going to lower, the vapor pressure is going to lower, and you're going to be able to boil at lower temperatures. All right, moving on, we'll talk about flash drying. Flash drying is instantaneous drying by contact with the hot air stream during conveying. So this is going to be direct drying. Vacuum drying, indirect drying. Flash drying is good for large capacities. It's good if you have a product that can withstand high temperatures. It also will allow you to get an end moisture content of less than 5 and sometimes down to less than 0.1%. I just want to note that there's two flash drying technologies that I'm not going to be discussing today later on, but that are definitely good technology, and that's fluidized bed dryers and spray towers. They're both flash drying technologies that work via the same standard, the same operating principles, excuse me. So here you can see you've got your hot air in your product, direct drying, very similar to as we previously discussed. So one question that often comes up during discussion of flash drying is, why won't my product melt? You've got your hot air coming in here, and your hot air, or burn, excuse me, or do whatever other negative changes could possibly occur. But you've got your hot air coming in here, and you're going to be transferring energy into the product. Could that have negative effects on your product? And the answer is, it depends, but most likely no. So what's going to happen is you're going to feed in your product, and it's going to look something like this. You're going to have surface moisture and probably some sort of internal moisture. As you heat up that product, this surface moisture, or this entire mass, the moisture and the product and everything is going to heat. It's going to heat and heat and heat until you get to the boiling temperature of whatever liquid you have. Once you get there, any more energy that goes in is going to be used to boil off that liquid. So you're going to be continuously adding energy in, but that energy is not going to go to heating the product because you can't heat the water up above whatever the boiling point is. So you put energy in, boiling off, boiling off, boiling off. This will happen until most, if not all, of the surface moisture is boiled off. What's going to be left is any sort of entrapped moisture. Getting this entrapped moisture can require higher product temperatures. It can depend on your product too. So, if you only want to get off some of that loose moisture, then I would say no. But, and it depends on from product to product too. You can feed in very hot for flash dryers. So there's a whole lot of variables, and it can be very dependent on product. But I want to make another good point, or two or three good points on this slide. The other is that this is going to be minimal product heating, and it's also going to be your constant rate drying phase. Going on as you continue to dry your product, you're going to be seeing product heating, and you're also going to be entering your falling rate drying phase. So that's a good thing to note. The other thing is that for water, we often use 120 degrees C as a good estimate for the outlet air temperature, and that your product is going to exit the dryer too, and it'll be slightly higher than 100 degrees C. So those are kind of standards that we use as an estimate, and it kind of gives you a good reference point. And then I think I hit on this, is that for low moisture content products where you have a ton of moisture that's entrapped within the product, you might need a higher temperature out. So moving on to the last type of drying that we'll be discussing, active freeze drying. Active freeze drying is good for ultrafine and nano materials. It's good for temperature-sensitive products. It's good for delicate structures. It's good for things where you want to preserve the color and the taste in living organisms. Often, these types of materials you can't heat because you will destroy important properties. Composite materials for the same thing, and solutions and dispersions are often commonly freeze-dried as well. Looking at this slide shows a good point I would like to make, and that is that solid concentration as a variable can have large effects on how much energy is going to be required for your system. What this shows is as you vary the percentage of solids in your feedstock, you can greatly vary how much energy you're going to have to put in for drying. So if you start, say if you consider 10% solids, if your 10% solids are 100 kilograms of dry material, that's going to be coming into your system with 900 kilograms of water to evaporate, which is a lot of water, especially if you consider that water is not easy to evaporate. Think back a couple slides to the energy requirements. Now, say you can also maybe operate that at 20% solids, which, might not sound like that big of a change, but really, this can make a huge change on your system. You're now going from 900 to 400 kilograms of water to evaporate, which can be a really big change. And you're talking about less than half of the energy to evaporate off that water. So this is an important slide. Moving on, this slide gives you a little bit of just the generalizations comparing batch and continuous. Continuous dryers tend to be flash dryers. They tend to be used for larger throughputs, and they tend to have lower residence time for the material within the dryer. When you're looking at batch dryers, you tend to have vacuum dryers. You tend to have smaller throughputs, and you tend to have longer residence times. And those residence times can be important when you're looking at your final moisture content. So when you go to select a dryer, we tend to think that there's two ways to think about it. You can think about selecting the dryer based on your product, or you can think about selecting the dryer based on the process that you need. So if you're going based on the product, you're going to look at the product form and the product feed form. So what are you feeding in and what are you getting out? You're going to look at the solid and liquid temperature property, the solid and liquid properties, for example, temperatures. You want to look at the initial and final moisture content. Other things to consider will be the toxicity and any other safety hazards. If you go process-based, you can just say that you want a continuous or a batch process. You can base it, well, I guess all processes will be based on throughput and production capacities. Product changes is an important one. Some systems can more readily handle changing from one product to another. Evaporative load is important, and upstream and downstream process fluctuations. Some systems can handle that more easily than others. So what this is a typical vacuum drying system. The product is going to come in here, and you're going to have your vacuum drying vessel here. For this example, it just happens to be a mixer. So you're going to have a mixer, and your product is going to come into the mixer. This mixer is going to be under vacuum, and the vacuum pump is here. Your heating media, what's going to be providing the energy for the drying, is going to be coming in through the jacket here, and it's going to be the energy is going to be conducted through the wall of the vessel and into the product. For this example, we've got a mixer, and the mixers work well for this because you are keeping the batch in motion. So the energy, instead of only going into the product is here, as the product is mixed, it's going to be coming, the product is here, might be here later. So you're going to be heating the entire batch rather than only heating the material next to the wall, and then once that material gets heated, it would work its way in. But by mixing, you can heat the entire batch at the same time. So you've got your mixer, you've got it's heating, it's evaporating, your vapor's coming off. Your vapor's going to come out, it's going to be filtered to leave your dried powder, your dust behind. It's going to come in, and this right here is it's going to be your primary condenser. So this is going to have cooled media running through it. It's going to chill the air, and your condensable load is going to go from a vapor and back into a liquid. This liquid will then fall into this condensate receptacle. Following this primary condenser, you're going to have your vacuum pump, which is going to be providing the vacuum for the system. You're then going to have a secondary condenser. This secondary condenser is going to allow you to collect any remaining solvent in the system. This solvent, what happens is because you are condensing at a different pressure, you're going to be able to obtain more solvent at the same temperature. So this solvent will be removed from the system and collect in a separate receptacle. 4 and 7 indicates, or what they symbolize is basically your solvent recovery system. So if you need more solvent, or if you want to reuse your solvent in your system, or if you can't, send it out into atmosphere, then this is going to be the solution to, recapture that. We talked about the dryer. Typically what you want is the full batch in motion for good heat transfer. You don't want the product just against the wall to get dried. You want the entire batch of material to get dried. Gentle mixing is important for many vacuum dried products because you don't want product breakage. You want the product size in to equal the product size out. So you want a gentle process. Another good thing with batch dryers is that they can handle variable feedstocks. So you can feed in slurries, paste, and damp powders, and you might change the time that you need to process, but it's not going to change the way the machine operates. The machine will operate the same. It'll dry your powder. You won't have any problems, and this can be a real advantage. For an example for vacuum drying, we'll talk about catalyst production. For catalyst production, you often start by preparing your base or your carrier material. This is often done with mixing, drying, and homogenization. During these steps, you can add the material in, you can blend it, you can do what's required. This is going to be your, just the base material for your catalyst. Often followed by that, you're going to impregnate the carrier material with the active. So often what this is, you're going to have the active, and it's going to be in a solution. You're going to spray that solution onto your base or your carrier material. You're then going to mix the mixture, and that's going to allow that active and that carrier fluid to coat all of your base and carrier material. Excuse me, it's bad terminology. So you've got your carrier material coated by your carrier liquid and your active material. Often what you're then going to do is you want to remove that carrier fluid. So you will then use the system as a vacuum dryer, and you will evaporate off that carrier fluid, leaving behind the active bound to your carrier material. Following that, you can activate or passivate, if needed, the active sites, and this is done usually with heat treatment using the jacket of the vessel to provide the heat energy. For catalysts, you can regenerate. You can just repeat the steps. You can add more active material, and then you can activate again. This is some examples of vacuum drying. There's plenty of other applications out there. Hopefully you guys are thinking of some right now. Shown here is a typical flash drying system. If you look at the flash drying system, the product is going to be coming in at item 1, and it's going to be pumped into the system by item 2. For flash drying, you you can add the material into the system in a couple ways. Shown here is an auger, often used as positive displacement pumps, and you're going to be adding the material in. This can also be one of the things that trips people up. Like a few slides back, I talked about being able to handle variable feedstocks in the vacuum dryer. You add them in, and the unit will work the same. Here, you may have this mixer, and it could be configured for a certain type of material, but once you change product or change process upstream, this may no longer be a suitable feeder, and this should be considered. So you're going to feed the material in. Your air that's going to be providing the energy is going to be coming in through item 8, and it's going to be heated up in item 7, which is going to be in this instance, it's a direct fired heater. So you're going to be pumping the air into the system. Your product is going to be coming in. That air and the product are going to interact. Now I'm going to go ahead a slide. For our flash dryers, what we use, and it's common for many, is an agitation mechanism. The agitation mechanism, the idea is that you want to separate any sort of agglomerates that are coming in so that you can get individual particles surrounded by the water rather than clumps of particles in water. This is going to give you better contact of the water that you want to remove with the air, so you're going to be much more efficient at getting the heat transfer into all the water. So you're going to come in, you're going to be dispersed, the air is going to come up and it's going to interact with these dispersed particles and it's going to evaporate off all the liquid. Your fine dust is going to leave. For this machine shown is a dynamic air classifier. What this is going to do is any larger particles are going to get rejected. The theory behind this is any particles that are either held together by moisture or not dry, so if they look something like this, they would be rejected and they would be sent down to be redispersed. So going back a slide, you have dried your product, you're coming out through the classifier. You're going to be coming up, you're going to have a bag house which is going to collect your product. The water vapor is going to continue on to the blower, and then you're going to have a discharge silencer. I kind of already hit on this slide, so we'll just say it again. This is your typical flash dryer. Often you're going to have dispersion to get better contact between the air, which is going to be providing the energy, and the moisture content. This is an interesting slide, and I think it's interesting to consider as well, that as you change your inlet air temperature for a given amount of air, you're going to be changing the amount of energy that you're adding into the system. So often, different equipment is going to be volume limited, so you can only put so much air through it. So by increasing the temperature of that air, you can effectively add more energy into the system. So what this shows is, say you have a cubic meter of air that your system can take. If you were to feed that cubic meter of air in at 150 degrees C and then your discharge temp is 120 degrees C, you're only going to be capturing 30 kilojoules of energy. But say you took that same cubic meter of air and you fed it in at 350 degrees C, you're then going to be extracting 230 kilojoules per cubic meter. As that energy goes from your heating media into your product. So you're getting much more energy out of the same amount of air. And you're also, importantly, using less air. Oh, excuse me. What this slide shows is recapturing some of the heat from the process. What you're doing here is you're taking the exhaust from your system and using it to heat another airflow that may be in your facility. So your exhaust air is going to be coming out at 120 degrees C. Your incoming airflow might be at 10 degrees C. What you can do is maybe heat that incoming air to 60 degrees C, and at the same time you would be cooling that exhaust stream to 70 degrees C. So this is another way that you can save energy in flash drying systems. What this slide shows is an example for calcium carbonate. You've got a feed that's going to have 35% solids, and what you want to discharge is 99.9% solid. So you're going to be going from 65% moisture down to 0.1% moisture. if you consider a dryer with an inlet temperature of 325 degrees C and an outlet temperature of 120 degrees C, your energy requirement is going to be 8,450 megajoules per ton of dried product. Now you can change certain parameters to decrease this energy requirement. The easiest one is going to be to increase the percent solids in your feed. So just by going from 35 to 65% solids, you can use much less energy and see significant savings. Now, often this is going to have to be done with another piece of equipment. So you're going to be balancing saving energy versus the energy of adding a second piece of equipment and the cost of operating and installing and purchasing that equipment. So even though you can see significant energy here, it should be considered that this is going to require some additional work. Now, also what you can do is you can simply increase the temperature of your feed. If you go from 325 degrees C to 650 degrees C, you can use 6,575 megajoules per ton of dried product, and you can see savings. This is going to come from, requiring less airflow. It's going to allow you to operate your system more efficiently. Another thing that happens when you use less airflow is that your ancillaries will be smaller, so your bag house and your blower. So this can be good in other ways as well. Now the ideal is to do both. So you want to feed in less water and then you want to operate at a higher temperature, and that's going to be how you find the way to operate your flash drying system most efficiently. This shows some applications for flash drying. As you can see, they're pretty varied. So our final drying technology that we'll be discussing is freeze drying. Freeze drying, the goal is going to be going from a liquid to a solid to a vapor. So starting at atmosphere right here, or standard conditions, which is 1 atmosphere and about 20 degrees C, you're going to first cool the system. You're going to go from a liquid to a solid. Once you have a solid, what you're going to do is decrease the pressure. Once you have the pressure sufficiently decreased, you're going to heat the system so that you cross from a solid to a vapor. Now, if you note, you want to decrease the pressure such that once you start heating the system, you don't pass through this green area. The goal is to go directly from a solid to a vapor, no liquid. So you want sublimation. You don't want to melt the product and then evaporate the product. That would be often detrimental to products that need to be freeze-dried. Freeze-drying is a very complicated process. What often happens is as you freeze the material, you're going to form a lattice of ice, and within that lattice is going to be your product. As you dry your product, what's going to happen is that lattice of ice is going to be removed, but you're going to have the product is going to be kept behind in the place that it would be in that lattice. So often what you see is you see a porous structure or a fluffy powder left behind. And this can be a little bit of a challenge. You can see here we obtained a well freeze-dried product, and it left behind a porous structure where all this empty space would have been the ice. And here, what you have is you have a solid structure that was dried, and this is going to be something that we like to avoid for freeze drying. So there's a couple ways for freeze drying: conventional tray drying and then active freeze drying. For conventional tray drying, you're going to have a large chamber, and within that chamber are shelves. Those shelves are going to be heated, and that heated shelf is going to be what's going to allow you to add the energy into your product. So you're going to pour the material into trays. Those trays are going to go on the heated shelf. You're going to pull vacuum, and you're going to freeze your product, or excuse me, you're going to freeze and then pull vacuum. You don't want to just pull vacuum. You would then just be vacuum drying. So you're going to freeze, and then you're going to pull vacuum. Once you have suitable vacuum, you're then going to add heat through the shelves, and that's going to be evaporating your product. The active freeze dryer is going to work very similar. You're going to put your product in. You're going to freeze the product, pull vacuum, and then heat it. For the tray dryer, you're going to have a lot of handling. Your product is going to be stationary in the dryer. So it's going to be in those trays, and that heat is going to come up through the bottom of that tray, and it's going to heat up the product. So the product is stationary within that tray. And because it is, when it comes out of the dryer, it's going to be in the shape of that tray, most likely. And it's going to come out in large lumps. At the end, you often have to crush or mill those lumps or those shapes down to get the smaller powder back that you want. And then this shows an API that had been milled after being freeze-dried. For the active freeze-drying, your product is going to go in, and I've already explained this, so I won't go into it again, but you want the product in motion as it's being freeze-dried. What happens here is instead of coming out as a big lump, you can often end up with a powdery substance that will discharge from the vessel or filter rather easily. And by keeping the product active, you can often get a different type of product out. So this shows the temperature curve for active freeze-drying. You're going to start out at about 20 degrees C in atmospheric pressure, and you're going to introduce a freezing media, which is going to drop the temperature of your product very low. Once your product is suitably cooled, you're then going to draw vacuum. Once you have vacuum, you're then going to start transferring heat through the jacket of the unit into the vessel, and that's going to transfer heat into the product. As you gently heat the product, you're going to see sublimation occur as the product, or as that frozen mass. You're going to see the whatever solvent you have that was frozen go from a solid to a vapor, and that over time is going to dry out your product. Often this is done stepwise, so you will heat, hold, heat, hold, heat, hold, and that's often very similar to how it's done in tray drying as well. And this is just another slide again showing the active freeze-drying process. As you freeze and reduce the pressure, you're often going to increase the amount of material you have. Once you have that frozen mass at that low pressure, you're going to add heat for sublimation. As you are actively freeze-drying the product, the ice granules are going to disappear. They're going to turn into vapor, and they're going to leave behind a fine powder. Because the batch is in motion, those powder particles will be picked up in the air, and they will be carried out with that vapor, and they can then be separated from the vapor, normally with the filter, leaving behind a reduction in volume. And eventually, you will end up with an empty active freeze dryer, and your particles will be, captured in a separate location. So these are some common freeze drying applications. As you can see, they're also pretty wide and varied. All right, so to close out today, we'll just give a quick comparison of technologies. Vacuum drying is a batch operation. It's going to allow you for precise environmental control. It's a gentle drying comparatively. It's got low energy requirements. You're going to have another thing which I didn't mention, which is nice that it's mentioned here, is you're going to have good cleanability. You can clean in place and sterilize in place for food and pharma applications. For flash drying, you're going to have continuous operation, and this is also going to allow for a large capacity. You're going to have rapid moisture evaporation and a low end moisture content. And then finally, for active freeze drying, the goal is to produce a uniform and consistent quality material. It's well suited for fragile and delicate structures, and it's very good because often it does not alter material characteristics that would be damaged in the other types of drying. So thank you for your time today. That concludes our webinar.